So thank you very much to have accepted me as a guest speaker in your session. So I will talk about temporal alignment of human motion. And this paper actually first of all, this paper is a collaboration with Peter Kahn from Technische University of Vienna. Peter Kahn is a computer scientist, is in a group of computer graphics, and Peter was working for a company who developed an application for tennis player to improve their play. So there were some professional and there were some non-professional performing the same movement, and the aim was to give feedback to the non-professional player in the sense that the movement of the non-professional was compared to the professional movement, and feedback will be then given. So the question of Peter came to me and asked me, how do I align in the best way two different movements of the same action, of the same motion? I'm a mathematician, and geometer, so I needed to understand this task in a geometric point of view. So that's the first thing I would like to explain to you. So what the task is to synchronize action. You have two ways of performing one action, and you want to synchronize it temporally. That's what we call temporal alignment in this setting. There are many ways to do this, and you can use feature of the movement to align them together. You can do it all in one, so align a combination of feature, or you can align feature by feature, and then obtain an average reparametrization of your motion, or diffeomorphism for those who are mathematicians in the room, that take into account all alignments of features separately. But yeah, what does it mean actually? What are the properties that temporal alignment procedure should have? So first of all, if you want to cook a procedure that takes two videos and align them. So if you take the same video, of course, you have nothing to do. That's the first thing, okay? This is called in mathematics reflexivity. Reflexivity. A motion is aligned to itself. By the way, that's the forecast for today. The forecast for tomorrow is this one. And here you see I have two channels of information. I have the picture of the video of the map of France, but I also have some sound, some noise, some person tell me the story that goes with it. Of course, you want these two channels to be played simultaneously. So you want to align one channel with the other. And of course, if you do it the reverse way, it should be the same. Yeah. If one channel is aligned to the other, and the second channel will be aligned to the first one. This is symmetry. Of course, if you know, on YouTube you can change the rate of a video. Some people use it. My mother uses it when she's looking at something in English. And of course, if you reparametrize a video with, for instance, you divide the speed by 2, then you know how to come back, of course. So if a first video is the outcome of if a video M1, a motion M2, let's say, if M2 is the outcome of the reparametrization of M1, M1 is also a reparameterization of M2, and you know exactly how. So if you started with a video, then you created a new video with half of the speed, then you will come back by multiplying the speed by 2, right? So this is the action of the inverse. So there is an action, a group action acting on videos. That's what I'm talking about here. And there is also an equivariance behind this. If two videos are aligned, and then you reduce the speed of both of them by 2, let's say, they will still be aligned. Meaning that if you play them simultaneously, it will still be aligned. There will be, the movement will be synchronized always. So this is the equivariance by the group action. The group action, here is a group of temporal reparameterization. So if your video is played between time t equal to 0 to time t equal to 1, then it's a group of diffeomorphism of this time interval acting on videos by reparameterization. So now you have, let's say, 3 different channels. You have a person is speaking here. There is a translation here in sign language, and there are subtitles. And you want all these channels to be synchronized, of course. So now, if you start with to align the speaker with the subtitles, and then the subtitles with the person translated in sign language, then you want, at last, that the speaker in sign language is also synchronized with the first one, sorry. So there is a triangle. If you start synchronizing one channel with the other, and then the other with the third one, then when you come back, you want it to be synchronized with the first one. Otherwise, there's no solution. This is called transitivity. So there are mathematical notion behind this, and it's turned out that there is a geometrical picture, and so there is a notion of fiber bundle behind this, and actually finding a temporal alignment procedure is exactly defining a slide for this fiber bundle by the action of given by the action of the group of reparameterizations. For instance, what will be a slide? You take all your channels, they give you information at different speeds, and you put you transform, you reparameterize all the channels so that the speed is constant. It will mean that, for instance, in my case, I will speak at constant speed. Yes, you do this with all channels. So, for instance, the subtitles are shown each word at constant speed. So all this channel then will be, well, synchronized, right? But you don't want to hear that. You don't want to see that. You want something which is real, okay? But this parametrization by constant speed is exactly solving your problem. It's aligning all the channels. But you want to have something which is natural. So for instance, the speaker should keep his speed of voice. So then if you have this slide of constant speed parametrization, then you can act by diffeomorphism to recover the speed of the speaker. And then all the other channels will be synchronized. I'm not sure this is very clear, but you can ask me a question after that. So perhaps I should have put this beautiful picture. So in blue, so the reference, for instance, you have one speaker or one tennis player, which is a professional. He speaks at this, the movement is perfect, or the speed of the speaker is what you want to have. And then you parameterize. You have a slide which are all those in blue here, other motions, all the speakers, or the tennis player, and you want, so for instance, a non-professional speaker or a non-professional tennis player will have a different speed of play or a different speed of speak. You will reparameterize the motion to come closer to the reference in this setting. How is defined close is also very important, but that depends on the application. Okay. As I said, you can, in order to have a concrete example, I will perhaps explain how. So now the data set that I had was a data set of tennis players. So I had exactly the movement of all the bones and all the joints of the tennis player. So there was a lot of different features that I could use. I could use the speed, I could use the rotation, I could use the angles. So this gives us a lot of feature. And so there were, for instance, the first thing I was thinking, well, this tennis player is doing this kind of movement over and over again. It's always a bit different, but very similar. So the first thing I thought, yeah, but when the arm is high and when the arm is low, these are keyframes. These are very specific time that's characterize the movement. So just align these keyframes from one player to the other. So this is here detecting this particular moment with something really important happening is called detection of keyframe. And then from one movement to the other, from between different players, we can just align these particular moments. This is the first thing that we tried, and it gives good results, actually. So it's really a simple solution giving a good results. But then you can also add more information and align continuous feature, but you want both. You want to be able to combine. So here, for instance, as I said, detection of the elevation of the arm and detecting where the arm is the highest, the lowest, for two different movements. So there is a one in red and one in blue. I don't know if you see it well, but anyway. And after alignment, these peaks are aligned. And we are using for this a piecewise linear map. Here, reparameterization are diffeomorphism of 0, 1. These are strictly increasing map from 0, 1 to 0, 1. So very simple object to understand with very complex properties. So in this case, we align keyframes, so we get something which is piecewise linear. It's just the piecewise linear map connecting association between special keyframes. But we can also align, for instance, here it's alignment of the arm holding the racket. So there is the arm holding the, so the hand holding the racket, connecting to the center of the body, is performing a movement. So there is a vector giving you the position of the arm. And if you normalize this vector, you get a curve on S2. And so here you see two different motion. On the first line, one motion, and on the second line, another motion. And if you compute this vector connecting the center of the body to the arm, you get two different curves on the sphere. And you want to align them the best, so make the best correspondence between the points on the sphere. And so this is before alignment, and this is after alignment, using some geometry on the sphere. So just basically we minimize here the distances between the curve, 5 minutes. So what we get now is not piecewise linear, is more complex diffeomorphism. So here the diffeomorphism, so a map between 0, 1 and 0, 1. There is an associated frame correspondence because the movement of the first player perhaps is taking 100 or 1,000 frames, and the movement of the second player is just 60 frames. So it's not the same domain and codomain, but from the diffeomorphism here we can compute it's trivial to have the frame correspondence. Okay, so how do we do this? How do we do now incorporating keyframe and also continuous matching? So we develop something which we called entrode dynamic programming. So usually behind the programs that gives us the alignment, there is a minimization of cost. So what you see, these squares are profile of cost function. And what you do is you want to find the paths that minimize the cost between all possible paths from one edge to the other. So there is a cost profile. The cost here should depend only on local feature, on local feature, and then the cost is an integral of what's happening locally. So now to incorporate keyframe, so there are, you see here the keyframe are correspondences between, so given correspondences between time in the domain and times in the codomain. So you want the path to go through these points or nearby. So if you see here, there is some flexibility. Here the condition is strict, there's zero tolerance. You ask the path should associate frame number 20 with, from the first video, to frame number 100 to the second one. So in the zero tolerance case, you constrain your solution to pass to key points in this square. You can add some more flexibility or completely non-constrain the system, but then it will not pass through will not associate the key moments of your movement as you want it to be. So in the first square here, probably the moment where the first arm will be the highest will not be at the same time as when the second player will have his arm at the highest. But if you constrain it, so adding, what we do is we add infinite cost in some region of this square, then you also constrain this key frame correspondence. I hope I will have, I have time to show you the video. So here, for instance, we start with a movement which was actually artificially constructed. It is a reparameterization of the movement that is downstairs in green here. We just add some diffeomorphism, and then you see this movement here is happening here. If you apply usual dynamical programming, you get the second line, which is not very well aligned. But if you constrain it, you come closer to the ground truth. So now let me escape here perhaps I can close it or do it small, and I will show you a video. Hopefully it will work. Okay, so the first, so that's 2 different players performing the same action at their own rate. So the first one is starting, the second one is starting a bit later, and we want to align these 2 different movements. So what we get is this one after alignment. I think it's a bit better. And if you want to, me to display at the same, oh no, I cannot do this. Yeah, to compare, I wanted to display it, but anyway, that's it. You saw, yeah. Let me play after alignment video again. Yeah. Thank you very much for your attention.
We are a little late, but questions? Yeah.
Yeah, I have a question about, actually, you may have different of morphology between the player. Taller one, a smaller one. How are you dealing with that kind of?
Actually, you deal it when you extract your feature. You deal with that, sure. So either you use the angles. So what I was presenting before was actually the direction of the arm to the center. So there's no problem. It's normalized. Yes, sure. Yes.
Any other questions? Okay, thank you very much.